Hello and welcome to another tutorial. We are looking at the switch and the switch statement, and we said that switch only allows specific types for the labels of the case. So these parameters that go into the case are labels, and we said that they can be expressions, but they have to be compile time expressions. So the Java compiler has to be able to evaluate basically the value of these labels at compile time. And we said that the strings are immutable, so obviously raw string literals are constants, compile time constants, they never change, right? So you can use them. So the string in switch expression is compared with the expressions associated with each case label as if the string equals method were being used. So when you use strings, the compiler actually compares the equality, right? We said that case compares the exact equality, and this just means for strings you say compiler says that month, in this case month is a variable, right? Or basically when we call the to lowercase, a new string is returned. So the new one basically it's like calling the dot equals on them. Remember, in Java you cannot use the equal operator to compare strings because that's reserved only for comparing the references, or you can assume pointers or memory addresses, right? So for exact equality or logical equality, you have to use dot equals. In order for this example to accept any month regardless of case, month is converted to lowercase. So usually when you deal with strings and you want to compare them, obviously if you don't know if the end user puts uppercase, lowercase letters, or a combination of them, you want to always convert to a particular case, like always use uppercase and always use lowercase, and that's the best practice. So when you're comparing strings in your code, I personally always try to stick with lowercase letters, and then whatever the input is, I convert it to lowercase and then compare only the lowercase. That takes the headache away of what happens if somebody puts the letters in uppercase or a combination of them. You don't worry about that, right? And all the strings associated with the case labels are in lowercase, right? So null selector variables. The selector variable of a switch statement can be an object. So this object can be null, right? And object, in this case, we said that obviously not every type. So the type of object matters. And we said that strings are some type that are allowed. Or enums, for example, are some types that allowed, right? Now obviously enum cannot be null, but a string reference might be null. So let's basically copy this. Let's copy this whole thing here, and maybe go back to our switch statement, create a new test here, public static void test5. I'm going to copy and paste this code here, and let's go with some month number, like let's say January, right? And as you can see, I used uppercase, and then we're converting to lowercase, and that therefore we don't care about the actual thing. We just want to make sure that the letters match, right? It's January, whether uppercase, lowercase, doesn't matter, right? In this case. So if I go ahead and run test5, and obviously I want to also print this month number, right? Just what happens. Note that we also have default. We don't really need this break after the default in this case. That's what we discussed before, because if the default is the last case in your switch expression, in the body of your switch statement, you don't really need to have a break after that, right? So if you run this, we're going to get 1 as expected. And let's see what happens. So this month, note that this month is a variable, and basically it's allowed, right? So we can use and we can also even say basically a string month lowercase is month to lowercase, right? And then we pass this one. All right. Now, as you can see, we are passing this variable here, but this variable basically, and then it compares this with different things, right? Now, this variable is object reference, so we can this can be null, in fact. So let's say month lowercase equals null. And now you see the compiler doesn't allow that. So that's a good thing, because you get a compile time error saying that month lowercase this variable cannot be resolved to all right, so as you can see, actually the compiler allows that. So you have a string type, and a string is allowed as the switch parameter. But if you set it to null, the question is what's happening here? Why are we getting a warning? Null pointer access. And the compiler realizes that, hey, you're switching over a null. The compiler says, I already know that this is null. So why are you switching over null? The variable month lowercase can only be null at this location. So let's see what happens if we run this. And we get a null pointer exception. And the compiler tells us because month lowercase variable is null. Now the question is, why is the compiler telling us it needs to so the error we're getting here is very interesting. We know that from Java 14, I believe, they added a more expressive way of for the JVM to tell you what's going on with the null pointer exception. And basically it tells you exactly where this null pointer exception happening, and it tells you that this variable is null. So the null pointer happens at month lowercase, this variable, right? And the compiler even gave you a warning, right? Said null point. So what's going on here? So the way it works with strings is that strings are objects, so they have this hashcode method. And the way the compiler compiles this for a string is that it just writes down the hash codes, and in the bytecode probably the hash codes are being assigned, because these cases are like buckets, right? And we know that this variable will eventually fall into one of these, and the easiest way to do is just check the hash codes, right? So if we look at the bytecode for this expression, let's see what we get. So if you look at test 5, test 5, right? Note that what's happening with strings. So we invoke virtual string hash code. So these are defining the month lowercase and up to here, right? And then it tries to invoke a string hash code. Basically, this string variable that we pass in, the compiler, basically the runtime, the JVM, gets the hash code and lookup switch. We said that switch transforms into a lookup table, right? That's why everything has to be a compile time constant. And note that these numbers are very interesting. What's happening behind the scenes. And for a string literals, what happens here is that the lookup table for switch becomes a hashcode lookup table, hashcode table, which means at compile time, the compiler doesn't care what is the string. It just calculates the hash codes. So obviously, if you have two different strings that result in the same hash code, then the switch is not going to work. But because strings are immutable and you can never override the hash code method in a string, you are guaranteed to have unique. So the question is the hash code method in the string guarantees that the two different strings never have the same hash code? And the answer is it could. I mean, it better, because otherwise this switch over the string literals is not guaranteed to work the way you want it, right? Because if you pass a string and the hash codes suddenly become equal to hash code one of the cases, but the strings are not the same, then you're in trouble. Your switch is not logically work the way you want it. But what I wanted to show you is that the way it works with switch statements is that for strings, what happens here is that it actually calculates the hash code, and it is still a switch on the integers. So in the bytecode there is no string, it's just integers, right? And we said that let me go back and find it again here. We said that basically what happens here is that this switching over strings translates in the bytecode, it translates switching over integers, which is efficient, right? Which is very efficient, because comparing integers is much more efficient than comparing strings using the dot equals method. That's why it makes sense. But again, the problem could be that The hashcode method does not guarantee that two different objects will have different hashcodes. What it guarantees is that if two different objects, you invoke the equals on them and it returns true, then the hashcodes must return true. That's the logic. However, two different objects that are not equal might give the same hashcode, right? But for strings, I guess the strings are finals. You can never override the hashcode method in strings, and I believe the way they have written it, at least they have confidence that two different strings will never give the same hashcode. That's why they allowed strings in the switch, right? So a string switch on the strings translates into hashcode of the strings, and that's just integers. I mean, it's not integers; it's probably just long. Or hashcode is integer, right? So it translates into a switch over integers, which is relatively quick and fast, right? All right. So this was the switch a statement, and again, null is allowed, object references are allowed, like wrapper types, character, byte, short, int, and we can also test that. Let's see what happens in the bytecode for wrapper types, or maybe let's just start with an integer type, for example, a primitive type. And then let's see what happens if you use a wrapper type. And then we already saw what happens with strings, but let's just have a general look at what happens in the bytecode for the switch statements. So public study void test 6. So I'm going to say int x equals 5 and then switch over x, right? And then we're going to have a couple of cases. Case, for example, 1, we're going to sys out basically 1, and then we're going to have a break here. Case 5, we're going to sys out 5 and then break, right? And then we're going to have a default, we're going to sys out anything else, then we're going to break, right? Again, we don't need this break at the end of default, but it's good to have. All right, so as soon as I save it, Eclipse is going to recompile and update the class file, so we can open this up and go all the way down to test 6. All right, let's zoom in and see what's going on. So iconst5 is for this literal, and then int variable I store 0. That's the first index of the stack. And then when we go to the switch, we have to first evaluate this parameter or expression, which means we have to load the value of x. So we say that I load an integer from which index of the stack? Index 0, right? So that's here. So line 2 of the bytecode is just hitting this, evaluating the expression of the switch. And now we're there. We have the table switch. Note that it's not a lookup table, it's a table switch. So switch translates into table switch. It's a table, which means we already know where the values are. Just quickly search this, and searching into tables, you can have efficient algorithms to search into that. And obviously we have case 1, 2, 3, 4, 5, right? And so case 1, case 2, case 3, case 4, case 5. Now this is very interesting. First of all, we have a default, right? It has a default which says jump to line 58. What is 58? Get a static out, and then load this constant, a string, anything else, and invoke the print line, and then that's it. And obviously we have a return here. Note that every break here translates jumping out of the switch, and after we jump out of the switch, there is no basically extra line of code, so we have to return, and we know that this method returns void. So instead of if returns a primitive, we say, for example, I return, but because it returns void, we just say return, right? So all these breaks eventually jump to have a go to. So for example, this break, it's the first break, and it translates into a go to line 66, and line 66 is when we hit this closing curly braces for the method, and we just return, right, without any specific value. If you say I return, it means there is an integer at the last index of the stack, and go ahead and return it. and obviously JVM checks that if the value on the stack is actually an integer. If it is, it returns. Otherwise, it gives you an error saying that the return type of the method is not compatible with the type you're returning, right? And we said that if the return type is void, you don't really need to explicitly write return here. It's not required. All right, so let me go back here to test 6. All right, so this first break translates into jumping to 66, which is just return because there is nothing else to do. Same here. After the second case, which is a string 5, we also jump to return. We just return, and we could very well just write return here. This still works because honestly the bytecode is pretty much the same here, right? So if we jump back here, you see that we have a return here. For this one, now it becomes a return statement or return instruction. This one is still a go to 64, which is also a return. So the nice thing here is that if you explicitly write return, then you don't. So if you write break here, then we get an extra instruction, extra line of bytecode that has to be executed, which is a jump instruction, and the jump is just return. So in this case, it's just very slightly more efficient if we explicitly write return, because we don't go through executing this line of bytecode, which just does a jump, right? So in these cases, yeah, I guess obviously you want to, more than likely when you have a switch and there is no line of code after that, you want to return something. Most likely you don't use return directly in your case, but you can use it, and then your bytecode becomes slightly more efficient. So again, all these breaks are basically translate into the jump. And then we said that the default is 58, and then after the default, this break doesn't have any instruction. There is because the compiler realized that after this break we hit here, you don't even need to write this break because the switch already ends, and after that it's return, right? So this break doesn't translate into anything. It doesn't translate to anything in the bytecode. So basically the compiler saw that you wrote this here and said that, okay, never mind, I'm not going. The compiler just ignored this line. It doesn't matter, which is good. I mean, the smarter the compiler is, the more it realizes that some lines of code you explicitly wrote it down so that the source code is more readable, but it doesn't translate to anything in the bytecode, right? And again, if the default is the last statement, you don't need to have this break. Now it becomes different obviously when you put it somewhere else. Now if we go back and basically we have go to and return. Now number 5 has the break of the last break, which in this case is for case 5. It does not translate into anything in bytecode. Basically the last case, even if it's a default case, doesn't have to be a break because you just hit the end of the switch body, right? So let me save this again. So for integer types, for primitive types, the expression is table switch, and it immediately writes the default, right? And then it's very peculiar what's going on here. So let's look at the bytecode. It's very weird that we didn't actually write down case 2, 3, 4, right? So we only had a case 1, case 5. But why is it that in the bytecode it also wrote case 2, 3, 4? That's very weird, right? And the reason is that, again, I mentioned that integers from 0 to 5 are hard coded in the basically in the JVM. So if let's say if I check change this to 10, let's see what happens to the bytecode. And now we have case 1, 2, 3, 4, 5, right? So the question here, why is it that we are still getting this kind of bytecode? It's very bizarre, right? So what's going on? So let's say instead of 5 here, we say case 10. Now let's see what happens next. Now we have case 1, case 10, which now makes sense, right? We have a default case 1 and case 10. So why is it that? So let's see what happens if I put 6 here and go down. We get case 1, case 6. So why is it so special about 1 to 5? And again, these are because we know that the integers 1, 2, 3, 4, 5 are very much hard coded. They have their own bytecode, icons. So JVM always prefers to basically when you if it sees any number from 1 to 5, it also puts the compiler also puts 2, 3, 4, because it really doesn't have any extra cost of having there, because they're hard coded. But any number after that, for example, instead of 1, if I have 6 here, now suddenly we have only 2 cases, right? 5 and 6. So integers 1 to 5 and even 0, these are special integers. So 0, 1, 2, 3, 4, 5 and -1. Now in this case, even with 0, we get 2 cases. So what about -1? So let's see, we get -1 and 5. So apparently it only works for integers 1 to 5. So if we have 1 or 2 here, for example, then we get 2, 3, 4, 5. It's very interesting that anything in between 1 and 5, the compiler writes everything in between. If I have only 2 and 5, it also writes 3 and 4. And 3 and 4 are also the default, right? So what if we have 5 coming first and then 2 coming later? Let's see if the compiler still does, yeah, it still writes case 2, 3, 4, 5, right? So 1, 2, 3, 4, 5 are special for integer, and that's because the bytecode is table switch. Now this bytecode instruction for the switch actually changes if you use another type like a wrapper. So let's have test 7 here, and then instead of int, let's use integer. And we know that we can take advantage of auto boxing. So I can use an integer literal and assign it to the integer object. This is an object, and this assignment operator is overloaded. But because Java doesn't officially support operator overloading, the name that they gave this kind of behavior was auto boxing. But the actual underlying behavior is called assignment operator overloading. But because Java doesn't promote operator overloading, they gave it another name, auto boxing. Now the code still compiles fine. Everything is exactly the same. The case can be still an integer literal. But let's go ahead and test 5, test 6, let's run test 7, for example, here. Save it. As soon as we save it, the JVM just immediately compile it. And let's look at test 7. Let's see what happens. So we know that 1 to 10, 1 to 5 are have a separate bytecode, but 10 we have to push it, right? Integer push. So it's not iconst bytecode, it's an integer push, and then invoke a static value of. So auto boxing means you call the static factory method value of, and we know that 10 is in the range of cached integers for the wrapper. So it just realizes that this value is cached, so it uses one of the cached integer objects in the memory, which is from -128 to +127, right? So this uses a cached integer. And then when we switch, we still get the table switch, right? And then default, and then case 2, 3, 4, 5. Case 2, 3, 4, 5. And we could also go with 1 here, for example. Then we get case 1 to 5, right? So the bytecode appears to be exactly identical when we use either an int equals 10 or a wrapper int equals 10. The switch bytecode is exactly the same. That's just because they've run this optimization that, hey, if you use a wrapper integer, just get the value out of it, right? So a load, know that the only difference here is that instead of saying I load 0, we first have to say a load 0, which means load an object reference, which is x, and now we have to extract the integer value out of it. Extract the integer, the int value out of it. And you know that in the integer class has a non-static member dot int value, right? That's why it's calling this invoke virtual, which means invoke a non-static method which returns an int, right? And the int value. So if you have a wrapper integer, you want to get the value out of it, the actual primitive, you say int value, right? And that's what the compiler did. So the only difference between a wrapper type and a primitive type in the switch is that there is one extra line of bytecode which happens behind the scenes, and it just extracts the primitive value that this wrapper class, this integer holds, and everything else is exactly identical. So you don't get any performance penalty on the switch if you use a wrapper, just because it just extracts the primitive value and then proceeds as usual, right? So I hope you enjoyed this lecture. Please stay tuned, and I'll see you in the next one.